Hi everyone. Sorry I couldn't make it today, but thought I'd record a little message for you. This isn't exactly the talk title, but I thought I'd just describe a story which is relates to instrumentation and astronomy, which is a biased and potted history of the Commensal Real-Time Fast Transients project and my involvement with it. All opinions of my own. Hopefully this will be a bit of fun. But I guess it's a useful story about how instrumentation and science can work together. So thanks, and a little disclaimer, and it's a bit of a story, like I said. So this is from my own flawed memory. Different people have slightly different memories of what actually happened in the end, so I encourage you to find out what other people think. I probably will miss some stuff, and sorry about that. Lots of people have been involved, and I can't really name all of them, so my apologies and my great thanks to all of them. And actually writing something like this is pretty crazy because you realize how long you've been doing it for. So one day when you've done 10 years of science in one thing, you'll realize that, oh my gosh, this is how I've spent a lot of my time. So anyway, it's a bit weird for me too. A little bit about me, how I got into astronomy. So I studied electrical engineering in UNSW in Sydney in Australia. I did my engineering thesis with an astronomer called Michael Ashley, and it was about remotely controlling a telescope in Siding Springs, an optical telescope. I really wanted to touch something that went into space, so I ended up getting a job. This is before Australia had much of an aerospace industry, and so I went and got a job where I was posted over to the UK, and I worked on military satellite communications. Unfortunately, I ended up being stuck on the ground, literally working on ground systems, and so never actually touched anything that went to space, although I did a bit of work on some space missions. And after 5 years, I came home inspired to do something more creative and exploratory than just plain engineering. And I'd always been fascinated with astronomy, and actually one of the last projects I did was working on the Dune mission, which now became Euclid. And I was really surprised at the time because we were tasked with doing some modifications of the whole mission design, and all the engineers were like, "Oh, this is great, we've worked it out." And I was like, "No, tell me what happens. What happens? How do we measure the curvature of the universe with this massive telescope?" Which is Euclid's a cosmology mission. And I was a bit shocked that the engineers didn't really care about the answer, and I was desperately keen to find out what the answer was. So I realized I probably needed to do more science with my life. So we came back from the UK. I was married in Australia, moved over with my wife, came back with my wife when she was pregnant. I had no job, no prospects, no money, pregnant wife, and I did the least responsible thing I could possibly do, which is I started a PhD in astronomy. I came home from hospital with a brand new baby, entirely free thanks to Medicare. You slap your Medicare card down and they give you a free baby. It's great. At home I got the letter saying my PhD scholarship had been successful, and in fact the stamp had a 50 years since Sputnik on it, which I thought was really cute. My first group meeting on my PhD was in March 2008 with I think 7 actually. Anyway, with Brian Gainsler in his office at University of Sydney, and on my way to that group meeting after being there literally for 5 days and not having a background in astronomy whatsoever. I'm a bit surprised they let me in, to be honest. I heard Shami Chatterjee, who some of you may know, talking to Brian Gainsler about some new result, and I realised now this was the Lorimer-Burst paper. And I recall, Shami was talking about Janskis and wondering, I had no idea what a Jansky was. And there was all this big discussion about what does it mean. And this really characterized the next 5 years of FRB science. But with Brian, I didn't work on that. Worked mainly on slow transient scintillation. And I was interested in FRBs, but I couldn't quite work out how to get my foot in the door. So I did a little experiment with a 12-meter telescope at Parkes, looking for FRBs coming from gamma ray bursts. We didn't find anything. I also looked at some techniques about how to detect FRBs with interferometers. And then, I was involved as a PhD student, and I was coming into the ATNF a bit, and the Australian Square Kilometre Array Pathfinder, or SKA, was being built, or was being designed at that time. So ASCAP had been funded, and I went to some of the early discussions where people were organising survey teams, and at the time, PhD students weren't really formally allowed to join the teams, but we sort of watched from the sidelines and found out what was going on. So Tara was doing the slow transients, and she still does, and Brian was still, I think, leading the polarization team, and still does. Peter Hall was at Curtin, and he was, which is miles away, at least it felt for me at the time, leading the fast transients team. And at that time, which became Kraft, at that time the Lorimer burst, which was the only electrogalactic transient. So IRATs were known about, and Peter and his team really put together a fantastic science case based on one source, which at the time was very controversial, to put it mildly. And they put together a really fantastic science case, really on thin evidence, which was quite compelling. So Kraft version 1 was these people. So JP McCarr, you'll see, is the lead author of that paper, and a very dear friend who sadly passed away several years ago. But it was really proposed by Peter Hall, Stephen Tingay, and JP McCarr out of Curtin, and they had a strong collaboration with JPL and Caltech. So there was some technical development that was required by ATNet to do, that Kraft needed ATNF to do to develop some capabilities in the ASCAP beamformers. And so the JPL and ATNF engineers worked together, but there was a little bit of friction between the ASCAP project and this team, because really they were asking for resources for what seemed at the time to be a not very compelling science case. Not so much no compelling, but the ASCAP was running late. There was obviously a lot of resources going into just trying to build the thing, and so at the end of this, I'll get to that point in a minute. Fortunately, collaboration between the west coast of Australia and the east coast of the US means that Sydney was a convenient meeting spot. So I actually attended a few of the meetings, and there was one in 2010 where I presented a flawed version of that diagram on the right, which I think I've corrected that version. But Larry Daddario, who was famous, very, very good engineer at Caltech and JPL, tore me to shreds. Now I'm building the very expensive thing, the Krakow thing. The Krakow instrument, which you may have heard of on ASCAP, is actually what I describe as the small field of view, or very expensive. I've gone with a very expensive option. But not long after that meeting, the JPL team had already put together some very good de-dispersion hardware, but ATNF and the ASCAP leadership told Kraft, basically, we can't do it. They said, our engineers don't have time. They're too busy just trying to build the basic modes, or put it another way, the modes that for Kraft and for Emu and Wallaby. We don't have time to do this Kraft thing, and so go away. And so it was low on the list of priorities, and maybe never. And so technical difficulties had already caused the project to run late. And so basically they said, Kraft, you're too hard, go away. And so that collaboration basically drifted onto other projects, and they were, I'm sure they were upset about that. But unfortunately, that was, what they were told. Now, around that time, at 2011-12, I had started a Bolton Fellowship at the ATNF. I was sharing an office with Ryan Shannon, who many of you may know. And in 2015, Ryan and Vikram had proposed to use Parkes, Murray Young at Parkes, to search for FRBs when the telescope was windstowed. And I've got to say, there's something about that guy. He just finds FRBs. So the first FRB, I think, was detected 1 hour and 21 minutes after the project started. I think the average rate for FRB detection at Parkes up to that point was 1 every 2 weeks of observing time. So that's, 1 every over 300 hours. And here he was, found it in the first hour and 21. In a slightly different project, they found another one, which was 120 Janskys, which is the brightest known one at the time, I think, with the exception of the Lorimer burst. I had, as is my wont, a heap of unpublished code, and one of those codes was to model a Parkes beam, and so they made use of that to try and to actually get a better measurement of the FRB luminosity. Now, because I was sitting in that room with Ryan, and he'd found that super bright one and used my code to actually measure the effective brightness of it. We did some back of the envelopes and worked out that a single ASCAP dish would have been able to detect the same burst. So I was helping without I was helping out with the ASCAP commissioning at the time, so they were just commissioning the interferometric modes and the beamforming and so on. The correlator wasn't working, so the antennas were basically just doing tests and most of the time were unused. And we worked out that this thing was detectable with a single dish. And then we also realized that if you could fly's eye or point all the antennas in different directions, you would be able to do a pretty good FRB survey. So by that time, I think FRBs were well established as being an astronomical phenomenon. And but we needed to find more of them. We wanted to measure what sort of luminosities they had and what sort of dispersion measures they had. And so there were still a lot of questions that could be answered by just doing a fly's eye survey, even for the brightest FRBs that would be quite nearby. But we had this problem. Craft had been deprioritized. There was lots of other stuff to do. We would be distracted anyway. So it would take months or years to get an FRB mode going, given the fact that we'd had, it had been shut down. Anyway, enter Andrew Brown, the defiant digital engineer. So I walked in to see Andrew at one point. Hi Andrew, can I ask you a ASCAP commissioning question? I think the point here is don't be afraid to talk to the engineers. Andrew says, blah, 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 geek, go on, unrelated stuff. Keith turns around and says, okay, thanks, Andrew. About to walk out of the office, and Andrew says, hey Keith, when are you going to test that FRB mode? It should be ready to go. When are you going to test it? So Andrew had actually built this FRB mode after all. Somehow, either he'd been defiant and literally said, well, I'm doing it anyway, or this whole thing that the ATNF management had told the craft team to go away and say it was too hard actually never filtered down to Andrew, and he'd built it anyway. So in either case, this mode was basically ready to go. So I would like to hand to Andrew the David Packard Medal of Defiance. Thanks to Andrew Down. So David Packard was the founder of a famous company called Hewlett-Packard. Hewlett-Packard famously really supports engineering and is a very engineering company, or at least it was when it was founded. And so once he actually gave a Medal of Defiance to this guy called Charles House for extraordinary contempt and defiance beyond the normal call of engineering duty. And I find that, I think that's a really useful thing to think about in terms of, engineering duty requires a certain amount of contempt and defiance. But, for extraordinary contempt and defiance, then you really get a medal from the founder of the company. Anyway, and to you, Andrew, hats off. Thank you very much. So I sort of backed out of this meeting with Andrew and ran kicking and screaming, ran up to the corridor and talked to Ryan and said, oh my gosh, we can do FRBs with ASCAP. Let's try and get that version 1 collaboration up and running. We sent an email out, and I think one person replied out of that big collaboration. They said, good luck. And that was as most we got from anyone. So with hindsight, I could have done this better. I probably should have picked up the phone. A few of us could have picked up the phone maybe. I was a junior guy. I was a bit afraid of these senior figures. But, they don't really bite. But email's a really terrible medium, so don't be afraid to talk to people, I think would be my lesson from that. Nevertheless, I write some GPU code. I mean, that was fun. I look at that code now and I'm horrified by it. So, I think one of the things you learn about this stuff is the code that you write 10 years on just looks horrible. Anyway, we wrote this GPU code to find FRBs, and we get this fly's eye mode running. So thanks to Malta McCarding as well, who realized that we might need a subarray so we could have our own fly's eye array, and that was running completely independently of all the commissioning activities. So we basically had run of the telescope on our own. And we could record data and process data, and by January 2017, we found our first FRB. So keeping up with the data was hard work, and even it was buggy, and that sort of stuff. So I went to this FRB meeting in February, and I think by that time maybe there was Arecibo had detected an FRB, and Parkes had detected the vast majority. And I went there saying, oh well, we're trying to do this thing on ASCAP. But we didn't actually have any results yet. And everyone sort of said, oh, you guys are kind of a waste of time. And because everyone was saying that at that point. A storm hits on the flight home. Aspen, by the way. If you get to go to a conference at Aspen, go to a conference at Aspen. At least if you get sacked from astronomy the next day, you'll always have Aspen. So I debugged this pipeline at a table at a restaurant, sleeping in LA because of this storm. Ended up sleeping on a bench. It was awful. Anyway, still no FRBs. Finally, I get home and I get this candidate clustering code working. And it turned, and my kids, I'm sitting next to my kids with my laptop on my lap, and the kids are watching Surf's Up, and for the umpteenth time. And then I see this plot of 170817, and that was our January detection. And it was such an exciting moment because we realized that actually we were onto something. As it turns out, that actual FRB had been detected well before that conference, and if I'd had that at that conference, it would have been like super cool to be able to talk about that. But anyway, didn't manage to get it organized in time. You never do. Anyway, so we started moving towards localization. So Ryan took over the observing, the operations. I'm working on the localization infrastructure, which is a lot more difficult. But we are collecting FRBs pretty quickly at this point, once every couple of weeks. And so we get loads of time, and the correlator's still not working. So the longer that takes, the more time we get. And then Ryan published this Nature paper about the de-influence relation. So the blue ones are the ASCAP ones, and the black ones are the Parkes ones. And you can see that if you take the blue ones from ASCAP and you move them away in Redshift, they collect more dispersion measure, which is the x-axis, and they get fainter, which is the y-axis. And that basically means they're the same population. You can see that basically those tracks more or less line up with the blue tracks, line up with the black ones. So we're trying to localize FRBs. So that's important because you find out which galaxy it comes from. I need to move over this way. This whole video thing is new to me. So we asked for 2 weeks of observing time from the director, which I think was Douglas maybe, to get our first localization. System was pretty unreliable. Shivani was working on stuff, and she had to sort of restart the code every couple of hours. Again, sorry. And after the end of 2 weeks, we got nothing. So we're due to hand over our operations to, hand back the telescope to operations. But the sysadmin is off sick, and the first thing they wanted to do was a software upgrade. So they give us an extra day. Late that night, Shivani restarts the code always because it just needs to be done. And the next morning, Ryan is looking at our Slack channel, and sure enough, there's an FRB there. So I sing screaming around the house, wake up the kids because I'm so excited because this is like the holy grail for us. And then we get the data, and we immediately split it in two. So I'm on the red team, and then the blue team is Adam Diller. And we both want to get to the point where we can localize this FRB and actually know exactly where it is. And so we both get the same position after a couple of weeks of working on it. And so we are pretty happy that we've localized our first FRB. In fact, this is the first FRB that was ever localized, once off FRB that was ever localized. So we get a few more FRBs. The Curtin group, who have already up to this point invested a lot in the craft collaboration, really need to get their just desserts. So JP starts working on the DM fluence relation, which is this relationship that basically not DM fluence, the DMZ relation. This basically tells you the density of the universe. So if you take an FRB, it goes bang, it's dispersed as it passes through the intergalactic medium, and so that dispersion tells you how many electrons it's gone through. So the further away the FRB is in Redshift, the more electrons it has to go through, and that gradient of that line essentially tells you the density of the universe. So after a lot of work, we finally get this paper out, and it goes out in Nature, and it makes a big splash. And then I got JP on the phone on the Friday and got to congratulate him, and we had a really nice moment actually. And I was really glad I made that phone call because about a week after that, JP sadly died rather. So there's a lot of highs and lows. So unfortunately, yes, he died shortly after that. So, we're doing the Craco is the very difficult and expensive thing. It's really difficult. It's always worth, so that's okay. It's okay to do difficult things and even fail at them. Try and fail quickly rather than taking a long time would be my view. Take time to phone people. You never know when you'll have your last chat. It's always better than an email. And if you can stand in someone's office and they turn around and say, "Oh, when are you going to do that thing, Keith?" Even better. All right. Thanks, everyone.